In this episode, we're going to continue our analysis on RC circuits. Last time we did it intuitively using our stomach. This time we're going to do it using our brains, using mathematics. So here is the setup. We have a battery of EMF E. It's an ideal battery, no resistance. And we have an uncharged capacitor and there is no current in the circuit before closing the switch. And we have closed the switch at time t is equal to 0. The question is, what's going to be the charge on the capacitor after some time t? Now if you figure out one of the quantities, like the charge, we can figure out the voltage across the capacitor. We can also figure out the voltage across the resistor and the current and everything. So all we need is one quantity, and in this episode I'm going to call that as the charge. Okay, so let's first think about this. We know that the moment we close the circuit, there's going to be a surge of current that flows this way, and that current initially has to be E by R. Intuitively we thought about that. But at time t, let's call that current as I. That's the value of the current right now. And because there was a current flowing now, this capacitor has been charged up. And let's say the charge on the capacitor is Q, and I don't know what Q is. I want to calculate Q as a function of time. That's going to be our goal. So to do that, we have to build an equation for this circuit. And the equation can be built using Kirchhoff's law. So let's start. I'm right now at this point, so the voltage at that point, let's call it as VA. I'm going to start moving in this direction. Notice I'm going from a negative to positive, so I'm going up in potential. So now when I come over here, I have plus E. And then I'm going to go down in potential because you see I'm going from positive to negative. And by how much potential am I going down? Well, I'm going down by a potential of Q by C. That's the drop in potential. And then I'm over here now. Again, I'll be going down in potential. Notice because I'm going in the same direction of the current, so I'm going down. Ohm's law minus IR. And in doing so, notice I have actually reached point A because there are no other potential drops anywhere in between. So I have reached point A. And therefore that should be equal to voltage A. And hence this thing should cancel out. This thing should be 0. And therefore E minus Q by C minus IR should be equal to 0. And this equation makes a lot of sense because the equation is telling me that the EMF is split up into two parts. One is the voltage across the capacitor and one is the voltage across the resistor. All of this makes sense. Okay, now we have to convert this into an equation for one variable. It seems like there are two variables, Q and I. Actually there aren't, because I itself depends on Q. Remember, I is just the rate at which the charge is flowing. Well, now I can also say it's the rate at which the capacitor is charging, because it's the same thing, right? If I find 5 coulombs flowing per second through a wire over here, 5 coulombs of charge will get deposited on this plate, so it's the same thing. And hence I can substitute that over here, and after substitution I'm going to substitute that over towards the right. I'm going to write that equation a little bit towards the right over here. And after substitution I'm going to get E minus Q by C minus dQ by dt times R equal to 0. And this is a trivial differential equation. You may or may not have solved this before, but it's quite trivial. This is a variable separable. Keep Q terms on one side, keep T terms on the other side. So let's do that quickly. We're going to get E minus Q divided by C. That's equal to R dQ by dt. And I don't like that C in the denominator. Let's get rid of that C. Let's multiply the whole thing by C. That gives us EC minus Q equals RC dQ divided by dt. And now I can, let's see what I can do. I'm going to continue over here. I'm going to get E. And so I'm going to get, I'm going to bring this guy down over here. So I'm going to get dt divided by RC. That's equal to dQ divided by EC minus Q. And now you see, notice that I have separated them and I'm ready for integral. So let's integrate this guy. Where are we integrating from? Well, integrating from time t is equal to 0 because we want to know what's going to happen since we close the switch, and we close the switch at t equal to 0 to some time t, and at time t is equal to 0, what is the charge? The charge was just 0, and the charge right now is just Q, and I want to calculate what that Q is. So I'm going to change colors now. What's going to be the integral of this? Well, that's just t, right? T minus 0, that's t divided by RC. And the integral of this guy is just going to be ln, because it's 1 divided by EC minus Q. So it's going to be ln, but then I have to take care of this minus sign, so I have to divide by minus sign, but I might as well just put that minus sign over here, and I have to take care of my limits. So this becomes T by RC equals minus ln, let's see, you know what I'm going to do? I'm going to take that minus sign, I'm going to throw it to the other side. Okay, that's better. You get EC minus Q when I substitute the upper limit, because that's just Q, and when I substitute the lower limit, I have to just substitute 0. Okay, I'm done with all the integration stuff. Now it's just algebra. So let's change colors again, and let's take anti-logarithms. So I'm going to get e to the power minus t divided by RC, and that's going to be equal to EC minus Q divided by EC. We're almost done. Okay, you can actually skip forward actually, because we're done. You just have to do some algebra now. So Q turns out to be, let's see, you get an EC, you can take it out, you get 1 minus e to the power minus t by RC. Ta-da! There we have it. Let me box this guy. So the equation looks very scary if you are seeing this for the first time, but it's not scary at all. You know what I'm going to do? I'm going to first figure out what the current is and the voltage equations and everything, and in the next video we're going to try and make sense of this. I think that's going to be easier for everyone. Okay, so what's going to be the current from this equation? Well, we just differentiate this, right? So the current I is just going to be the derivative dq divided by dt. And how do we derivate that? Well, we just multiply this over here, and so the first part of the derivative is just going to be 0. So you're going to get 0 because EC minus derivative of EC times e to the power minus t by RC. That's going to be EC into e to the power minus t by RC multiplied by the derivative of minus t by RC is going to be just 1 by RC. And let's see what we get because of that. So the current just turns out to be, or is it C cancels out, you just get minus E divided by R times e to the power minus t by RC. Ta-da! There we have it. Looks like another scary equation which we're going to box in. And finally, I want to calculate what the voltages are. The voltage across the capacitor, actually this is the easiest part. Okay, now just look at this. The voltage across the capacitor is just going to be Q divided by C. It's going to follow my charge, right? It's going to do the same thing as my charge. So the voltage across capacitor is just going to be, I just have to divide this guy by C. So it's going to be E times 1 minus e to the power minus t divided by RC. And what's going to be the voltage across the resistor? Well, the voltage across the resistor is just going to follow this guy, because it's going to be IR, Ohm's law. And so I've just multiply this by R, and therefore we get VR now as just think about it, you multiply it by, just get minus E times e to the power minus t divided by RC. So let's box both of these guys, and there we have it. We now have four scary equations, but don't be scared. I'm going to demystify these equations. I'm going to see how all these equations are eventually going to lead us to what we thought about and going to give us even more information. So stay tuned for more. We're going to continue in the next episode. Stay tuned.